Right now, 25,800 light-years away, something is stirring at the center of your galaxy. You cannot see it happen. No telescope ever built has photographed it directly, not once. But it moved before, violently, and it left scorch marks on gas clouds that are still glowing from the encounter centuries later. That is not even the strangest part of what is happening to the place you call home. You are moving right now over 1.3 million miles per hour toward a destination hidden behind a wall of dust and stars so thick that for most of the 20th century, astronomers pointed their finest instruments straight at it. Here is some of what is waiting to be unpacked in the hours ahead. A black hole that erupted bright enough to light up gas clouds tens of thousands of years across, and whose light is only now finishing that journey to reach us. A gravitational basin 500 million light-years wide, dragging entire superclusters toward it, with no confirmed source anyone has ever laid eyes on. A galaxy, your galaxy, slowly running out of the one thing it needs to keep making stars. From where you stand, the Milky Way looks calm, fixed. The kind of thing stable enough to build a civilization's entire sense of permanence around. Every measurement we have says otherwise. If the idea that your own galaxy is not what it appears to be keeps you up at night, hit like and subscribe before we go any further. Prepare yourselves. We begin. Put your hand flat on the table in front of you. It feels still. Your coffee does not slosh. The walls do not shudder. Every instinct you have built over a lifetime tells you that you are, at this moment, not moving at all. You are wrong, and the wrongness happens on 3 separate scales. Earth spins on its axis, carrying you in a circle at roughly 1,000 miles an hour, depending on where you stand. At the same time, the planet loops around the sun at close to 67,000 miles an hour, a full circuit every year, a path so wide that light itself takes 8 minutes to cross half of it. And underneath both of those motions, the Sunday with Earth and every planet in its grip is racing around the center of the Milky Way at something close to 500,000 miles an hour. One trip around takes roughly 225 million years. The last time our solar system was in this exact spot on that orbit, there were no flowers on the planet yet, no birds, nothing that looked back up at the sky and wondered what it was looking at. Think of a ship's deck at night, far out at sea, engines running, no coastline in sight. Stand on that deck and drop a coin. It falls straight down into your palm. Nothing about the motion of the ship shows up in the fall of the coin because you are moving with it. Earth works the same way. The atmosphere, the ocean, your own body, all of it rides along together, so the motion cancels itself out of your senses completely. But there is a 4th layer sitting on top of the first 3, and this one does not cancel out so neatly. The galaxy itself is moving through space, dragging the sun, Earth, and everything on it towards something out in the dark. That motion is the reason this investigation exists at all. So ask yourself what home is actually supposed to mean here. A planet that spins, circling a star that races. Inside a galaxy that is itself falling toward a destination it cannot see and colliding with a neighbor it cannot avoid, while quietly running out of the fuel that keeps it alive. Home, it turns out, is not a fixed address. It is a moving target with an expiration date, and we are only now learning how to read the countdown. What follows is not one mystery. It is 5 separate case files, each opened by a different team of scientists on a different continent, using instruments that were never designed to find what they eventually found. Some of those files are still open today, with the argument unresolved and researchers on opposite sides of the same data. Others closed only to reopen years later. More unsettling the second time around. The first case file starts with a hum that would not go away. A pair of engineers chasing down static in a New Jersey antenna, certain they had a wiring problem, certain the noise would eventually make sense. In 1965, two radio engineers at Bell Labs in New Jersey were trying to solve a much smaller problem than the one they stumbled into. Arno Penzias and Robert Wilson had a large horn-shaped antenna built to bounce signals off satellites, and it kept picking up a faint hiss, not from one direction, from everywhere. It showed up during the day and at night, in summer and winter, no matter where they pointed the thing. They checked every mundane explanation first. Faulty wiring, interference from New York City. They found pigeons nesting inside the antenna and cleared them out, along with what Penzias later called dryly a white dielectric material. The pigeons left, the hiss did not. What they had actually found was the afterglow of the universe itself. Light released 380,000 years after the Big Bang, stretched by billions of years of cosmic expansion, until it cooled into microwaves, arriving from every direction at once, because it fills all of space equally. Scientists call it a cosmic microwave background. Penzias and Wilson won the Nobel Prize for it in 1978, largely without knowing what they were listening to when they first heard it. For years, that background looked perfectly smooth. The same temperature everywhere you pointed. Then, in the 1970 seconds, more precise instruments found something the earlier measurements had missed. One half of the sky ran microscopically warmer than the other. The opposite half ran microscopically cooler. A pattern researchers named the temperature dipole. Here is the plain physics behind it. Stand still near a train track, and a passing train's horn holds one steady pitch as it approaches, then drops the instant it passes you. Move toward a sound source, the sound waves compress, raising the pitch. Move away, and they stretch, lowering it. Light behaves the same way. Move toward a source of radiation, and it shifts toward higher energy, which in this case reads as warmer. Move away. The only way half the sky reads warmer and the other half reads cooler is if something is moving through that ancient light. And the only something available at that scale is us. Once astronomers ran the numbers, the result was precise almost to the point of unease. The Milky Way, along with the rest of our local group, is moving at somewhere between 600 and 630 kilometers per second econ toward a patch of sky sitting in the direction of the constellation Hydra Centaurus. Put that speed into something you can actually hold in your head. At that velocity, you could cross the entire continental United States coast to coast in about 6 seconds. That is not an estimate built on assumption. It is a direct measurement, confirmed independently by every satellite that has mapped that ancient light since, from Kobe to WMAP to Planck. The number does not move. What the dipole could not do was tell anyone why. It handed astronomers a speed and a heading, and then went completely silent on the cause. Something out there was pulling the entire local group toward it hard enough to produce that exact number, and the cosmic microwave background had no way of saying what the tracks were laid out with total precision. Finding what actually made them meant leaving the oldest light in the universe behind and turning to a much harder kind of measurement, one that meant timing the motion of individual galaxies, one by one, across a region of sky nobody had mapped that carefully before. 7 astronomers took on that harder measurement, and colleagues who thought the project was reckless gave them a nickname that stuck: the Seven Samurai. Sandra Faber, Alan Dressler, David Burstein, Roger Davis, Donald Lyndon Bell, Roberta Turlevich, and Gary Wegner. Each one already had a career worth protecting. They spent the early 1980 seconds risking it anyway. Sandra Faber brought the theoretical rigor, the kind of mind that checks an equation 4 times before trusting it. Alan Dressler carried the instinct for pattern recognition that would later put his name on the discovery itself. The rest split the observing work across telescopes on different continents, comparing notes by mail and by phone in an era before either was fast. Their tool was something called the DN sigma method, a way of measuring the true distance to elliptical galaxies without depending on the universe's expansion to do it. Here is the idea in plain terms. Inside an elliptical galaxy, stars do not orbit in a tidy disk. They swarm in every direction, and the speed of that swarm, measured through the spread of their light, correlates tightly with how big and how bright the galaxy actually is. Measure that internal speed, and you can calculate the galaxy's true size. Compare true size to how large it appears from Earth, and distance falls out of the math, independent of redshift entirely. That mattered enormously because redshift alone conflates 2 things: how fast a galaxy is being carried along by cosmic expansion, and how fast it might be moving on its own, under the pull of nearby mass. The DN sigma method let the 7 samurai strip away the first number and isolate the second. What remained was called peculiar velocity, the leftover motion a galaxy has after you subtract the expansion of the universe itself. They expected that leftover motion to look like static, small, scattered, pointing in no particular direction, the kind of noise you would expect if galaxies simply drifted at random within their local neighborhoods. It did not look like static. Galaxy after galaxy, across hundreds of millions of light years, showed peculiar velocities pointing the same general way. Not identical paths, but a shared drift, the kind of pattern you get when something enormous is quietly organizing the motion of everything around it. By 1986, the team had enough data to publish. Their conclusion: hundreds of galaxies across the local universe were streaming toward a single, undefined point in the southern sky, all being pulled by something with the gravitational weight of tens of thousands of galaxies combined. Alan Dressler gave that unseen mass a name the following year. He called it the Great Attractor. The reaction from the wider astronomical community was not applause. Cosmology at the time rested on an assumption that the universe at sufficiently large scales should look smooth in every direction. No single structure massive enough to organize galaxy motion across hundreds of millions of light years. What the 7 samurai were describing broke that assumption outright. Critics questioned the DN sigma calibration. They questioned the sample selection. Some suggested the whole result was a statistical mirage built from a handful of unlucky measurements. The data did not cooperate with the skepticism. Independent groups, using different telescopes and different samples, kept finding the same coordinated drift, pointing toward the same patch of sky. The flow was real. The direction was consistent. Something out there had the gravitational weight to organize galaxies across a truly staggering volume of space. There was just one problem nobody on the team could get around, no matter how good their instruments were. When they finally pointed those instruments at the exact coordinates the math demanded, the sky in that direction gave them almost nothing back at all. Picture a dinner plate held up at eye level, tilted almost flat, so you are looking along its edge instead of down at its face. That thin, bright line is what the Milky Way looks like from the inside. We do not sit above the galaxy, looking down at its spiral arms the way every illustration in every textbook shows it. We sit embedded inside the disk itself, out near one edge, staring sideways through the thickest accumulation of stars, gas, and dust. The galaxy has to offer. That dust is the problem. Not fog you could walk through, not smoke you could wave away. Individual grains, smaller than particles of cigarette smoke, scattered so thinly you would never notice a single one. But stack that thin scattering across tens of thousands of light years of galactic disk. The cumulative effect stops visible light cold. Stars that would blaze in any other direction simply vanish behind it. An entire strip of sky, roughly 20% of everything out there, goes dark to any telescope working in ordinary light. Astronomers noticed the effect long before they understood the cause. In 1878, a researcher named Richard Proctor mapped the visible galaxies across the sky and found a band running through it where the count dropped to almost nothing. He called it the zone of few nebulae, and for decades nobody knew whether that band reflected something true about the universe or something true about our own obstructed view of it. Eventually, the answer became clear. The galaxies were there all along. Our own galactic disk had simply erased them from the record before their light ever reached us. Now, place the Great Attractor on that map. The coordinates the seven samurai had calculated, the point every peculiar velocity in their survey pointed back toward, sat almost exactly inside that blacked out strip. Not near the edge of the obscured region, where a little patience and a slightly longer exposure might tease out a signal. Dead center. Behind the single densest wall of dust and starlight the entire sky had to offer. Think of standing inside a dense forest, trying to make out a mountain range. You know he's out there somewhere past the tree line. You can measure the mountain's effects. You can feel the shift in wind, watch water drain toward it, track every clue nature gives you about something large sitting behind the trees. What you cannot do is walk to a clearing and simply look at it, because in every direction that matters, there is no clearing. That was the position astronomers found themselves in the late 1980 seconds. They had a calculated mass. They pointed the era's most capable optical telescopes directly at those coordinates and got back almost nothing. A faint smear of starlight, so heavily absorbed and reddened by intervening dust that no useful structure could be pulled out of it. The very thing that was supposedly massive enough to drag the entire local group across intergalactic space refused to show itself to the one kind of instrument built to find it. Seeing past that wall meant giving up on visible light entirely and turning instead to wavelengths that dust could not stop. Sound behaves differently than light when it hits an obstacle. Shout into a dark cave and the sound wave bends around the rocks blocking your path, bouncing off distant walls and returning information about a space your eyes cannot penetrate at all. Longer wavelengths slip past obstructions that stop shorter ones cold. Infrared and radio astronomy work on exactly that principle. Both use wavelengths long enough to pass through the same dust grains that swallow visible light whole, arriving at a detector largely undisturbed by the very material that had blinded every optical survey aimed at the Great Attractor's coordinates. The first real breakthrough came from space. The infrared astronomical satellite launched in 1983 and spent the following years scanning the sky in wavelengths no ground-based telescope could reliably capture. When astronomers pointed its results at the zone of avoidance, galaxies that had never appeared in any optical catalogue simply materialized, not faint smears distorted by reddening. actual structure, actual galaxies, sitting exactly where dust had made them invisible before. Radio astronomy pushed the same idea even further. Neutral hydrogen gas inside galaxies emits a specific radio signal, one that barely interacts with interstellar dust at all. Radio telescopes, tuned to that signal, could trace galaxies through the thickest part of the Milky Way's disk as if the dust were not even there. Piece by piece, a structure began to take shape almost exactly where the Seven Samurai's calculations had pointed. Astronomers named it the Norma cluster, catalogued formally as Abel 3627, sitting behind the galactic plane in the general direction of the constellation the cluster borrowed its name from. Norma turned out to be real, and it turned out to be big. Estimates placed its total mass at somewhere around 1,000 trillion times the mass of the Sun, roughly 10 to the 15th power in solar masses. That number belongs to one of the more substantial galaxy clusters known anywhere in the local universe. For a moment, looked like the mystery had closed. A massive cluster, hidden exactly where the missing mass needed to be, finally visible after infrared and radio instruments cut through what optical telescopes never could. Norma's mass, as large as it genuinely was, fell far short of what the observed motion actually required. The Seven Samurai's data demanded a gravitational pull strong enough to organize the drift of galaxies across hundreds of millions of light years. Norma alone could account for only a fraction of that pull, something on the order of 1/10 of the total mass needed to explain the flow. A real cluster, sitting in exactly the right place and still not nearly heavy enough on its own. Something else had to be contributing to that pull, and whatever it was not going to be found anywhere near Norma's coordinates. It was going to be found much farther out, in a structure so distant that for decades nobody thought to connect it to the mystery at all. The distant structure that would eventually answer that question had already been sitting in the astronomical record for more than half a century, filed away and forgotten. In 1930, an astronomer named Harlow Shapley was busy cataloging galaxy clusters, the kind of methodical, unglamorous work that rarely makes headlines but quietly builds the foundation everyone else later stands on. Shapley had already made his name years earlier by measuring the Sun's true position inside the Milky Way, correcting a mistake astronomers had lived with for generations. By the 1930 seconds, he was still counting, still mapping, still filling notebooks with the positions of distant galaxy concentrations nobody thought mattered much. One of those concentrations sat in the direction of the constellation Centaurus, far beyond anything considered locally relevant. Shapley logged it, gave it a designation, and moved on. For the better part of 50 years, it stayed exactly where he left it. Footnote: a coordinate, a cluster too far away to matter to anyone studying the nearby universe. Here is how far away. The Great Attractor region sits roughly 150 to 250 million light-years from Earth. Structure Shapley had catalogued, now known as the Shapley concentration, sits at something closer to 650 million light-years out. Call it 4 times the distance. Under ordinary physics, that distance should have made it irrelevant. Gravitational pull weakens with the square of distance, so an object 4 times farther away exerts roughly 16 times less influence for the same amount of mass. 2. By that math, whatever Shapley had logged decades earlier should have been background noise, drowned out completely by anything closer. Then, astronomers actually weighed it. The Shapley concentration turned out to hold something in the neighborhood of 5 times 10 to the 16th power in solar masses. Set that beside Laniakea's central structure, the the very basin our own galaxy sits inside, and Shapley outweighs it by a factor of more than 10. A cluster 4 times farther away, carrying enough mass to overcome that inverse square penalty, and then some. Mid-2000 surveys of galaxy velocities across the local universe made the implication impossible to ignore. Astronomers had assumed, reasonably enough, that once you accounted for the Great Attractor, the story was finished. The flow of galaxies should have converged there and stopped. It did not. Velocity field maps kept tracing that same coordinated drift straight past the Great Attractor's coordinates, continuing outward, pointed at Shapley the entire time. For decades, the working assumption had been simple. One attractor, one source, one answer waiting behind the dust. The real picture required 2, operating at wildly different distances, each contributing its own share of the pull, the nearer one shaping the local flow, and the farther one reaching in from 600 million light-years out to add weight. The closest structure could never provide alone. That discovery did more than complicate the map. It forced astronomers to go back and look with much harder scrutiny at the number the 7 samurai had originally assigned to the Great Attractor itself. Because if 2 structures were sharing the job of pulling the local group through space, the mass required from the nearer one was about to shrink considerably, and nobody was going to enjoy watching that correction happen. Go back to the number the 7 samurai actually published in 1986. To explain the flow they had measured, the mass sitting behind the dust needed to weigh in at several times 10 to the 16th power in solar masses. Tens of thousands of galaxies worth of material compressed into one gravitational source. That figure was not a guess dressed up to sound impressive. It was the only number the math would allow. Given the observed velocities, given the assumed distance, that was what had to be sitting there. Nothing smaller could produce the pull they were seeing. For close to 20 years, that number stood more or less unquestioned, because nobody had a good way to weigh the region directly. Then X-ray surveys in the early 2000s finally did the job properly, mapping the hot gas trapped inside Norma and the surrounding structures with real precision. Hot intracluster gas glows in X-rays in proportion to how deep the gravitational well actually is, which makes it one of the more reliable ways to weigh a cluster from the outside. The correction was not subtle. Actual observed mass in the region came in somewhere around 90% short of the original figure. Not a rounding error, not a revision at the margins. The number that had made the Great Attractor famous was, in plain terms, wrong by an order of magnitude. Sit with what that meant for the people who found it. The 7 samurai had staked their reputations on a discovery that turned out to be entirely correct. Galaxies were streaming together. Something massive really was pulling them. And the specific figure that made the whole thing sound so dramatic, the number that got the discovery its name and its headlines, did not survive contact with better data. Being right about the existence of something and wrong about its scale is its own particular kind of professional discomfort, the sort that does not come with an easy correction in the next paper. Here is what actually held up under the revision. The flow itself remained real, confirmed by every subsequent survey that looked. Norma remained real, a genuine cluster sitting exactly where the calculations had pointed. The basin, the broad region of enhanced density organizing that motion, remained real as well. What did not survive was the assumption baked into the original picture that one object, sitting at one location, could account for the entire pull by itself. As we saw with Shapley, the true source was already turning out to be more than one structure, working at more than one distance. The Great Attractor was smaller than advertised, precisely because it was never carrying the load alone. That left the field with a harder problem than simply revising a mass estimate. If no single object explained the motion, then the old approach, hunting for one dominant source and measuring its weight, was never going to produce an accurate map. Astronomers needed something else entirely, a method built not to locate a single attractor, but to trace how galaxies actually flow as a connected system across the whole of the surrounding universe. The two researchers who finally solved that problem were not chasing headlines. Brent Tully, astronomer at the University of Hawaii, had spent decades cataloging galaxy distances with the kind of patience that rarely gets celebrated in real time. Hélène Courtois, working out of France, brought the same discipline to the observational side of the partnership. Together, starting in the early 2000s, they began building something that had never existed before at this scale. A catalogue of galaxy distances and velocities precise enough and wide enough to map how matter actually moves across hundreds of millions of light years. They called the project Cosmic Flows. The technique underneath it was peculiar velocity mapping, the same basic idea the Seven Samurai had pioneered decades earlier, pushed now across a far larger volume of space with far better instruments. Measure a galaxy's true distance independent of its redshift. Compare that distance to what the smooth expansion of the universe would predict. Whatever motion is left over, the part expansion cannot explain, is the galaxy's actual physical drift through the gravitational landscape around it. Do that for one galaxy, and you have a data point. Do it for tens of thousands of galaxies, and you have something closer to a map of the forces shaping the local universe. Reading that map required a method borrowed from an entirely different field. Geologists, mapping how rainfall drains across a landscape, use something called a watershed algorithm, a way of tracing which slope sends water toward which valley and where the ridgelines sit that split one drainage basin from another. Tully and Courtois applied the same logic to their velocity data. Instead of water flowing downhill under gravity, they were tracking galaxies flowing along gravitational gradients, and instead of watersheds separating river systems, they were mapping the boundaries between regions of space where galaxy motion converged toward different centers entirely. What that analysis revealed, published in Nature in 2014, was a single coherent basin of attraction spanning roughly 500 million light-years across, containing something on the order of 1,000,000 large galaxies, all flowing along shared gravitational contours toward the same general region. Not a loose association of nearby structures. A genuine connected watershed, with the Milky Way sitting well inside its boundary. They named it Laniakea, a Hawaiian word meaning immeasurable heaven, chosen deliberately to honor the tradition of Polynesian navigators who once read the sky itself to find their way across the open Pacific without instruments. The name fit. This was in its own way a new kind of navigation, one that used the motion of galaxies instead of stars to chart a position nobody had ever been able to plot before. To make the scale of that discovery graspable, consider what it replaced. For most of the 20th century, our home address in the universe was the Virgo supercluster, a grouping of galaxy clusters loosely centered on the massive Virgo cluster itself. That address turned out to describe only a small piece of the real picture. Laniakea absorbed the Virgo supercluster entirely, revealing it to be one modest neighborhood inside a structure many times its size, with the Great Attractor sitting near Laniakea's gravitational core, still pulling, still real, just no longer mistaken for the whole story. Giving the Milky Way a genuine cosmic address answered a question that had lingered since the Seven Samurai's original data. It also opened one that turned out to be considerably harder to sit with, because even inside a fully mapped basin, 500 million light-years wide, with the Great Attractor and Shapley both accounted for, the numbers still did not quite balance. Something in the motion of our own galaxy remained unexplained, a small residual velocity that refused to disappear, no matter how carefully the map was drawn. Add up the pull from the Great Attractor. Add the pull from Shapley, reaching in from 600 million light-years out. Run the full calculation, every mass, every distance, every contribution the best data of the early 2000s could offer. The numbers still did not close. A residual remained, a leftover velocity of a few tens of kilometers per second econd that no combination of known structures could account for. That might sound small, next to a total drift of 600 kilometers per second econd. It is not small. At the scale of intergalactic space, a few tens of kilometers per second represents motion coordinated across tens of millions of light years. Motion that has to come from somewhere. In this line of work, a gap that size is not rounding error, it is signal. And signal demands an explanation. Yehuda Hoffman, an astrophysicist at the Hebrew University of Jerusalem, led the team that finally chased that signal down. Rather than searching for another distant cluster to add to the ledger, Hoffman's group applied a technique called Wiener filter reconstruction, a statistical method built to take incomplete, noisy velocity data and reconstruct the most probable three-dimensional map of the mass distribution producing it. Feed it the peculiar velocities of thousands of galaxies, and it hands back a model of the gravitational landscape those galaxies must be sitting inside, filling in the regions no telescope had directly measured. Run that reconstruction on the residual, and the result did not point toward a hidden cluster at all. It pointed toward an absence, a region of space carrying markedly less mass than the cosmic average, sitting roughly opposite the direction of the known attractors, quietly shaping the flow just as powerfully as any concentration of galaxies might have. Sit with that for a moment. For the better part of 3 decades, the entire hunt had been framed one way, something heavy enough somewhere out there to explain why the local group moves the way it does. Every method built, every survey launched, every telescope pointed toward the zone of avoidance was aimed at finding mass. And half the answer, once the reconstruction was finally sharp enough to reveal it, was not mass at all. It was the lack of it, a stretch of nearly empty space, its gravitational absence tugging on everything nearby in a way that mimicked, almost exactly, the pull of an object that was never there. Astronomers had spent decades hunting for something to weigh. What they eventually found was something to measure by what it was missing. A void doing the work of an attractor simply by refusing to hold as much matter as the space around it. That absence could not stay an abstraction in a reconstruction model forever. It needed a name, and it needed a mechanism, something that explained how a region of nothing could shove galaxies through space with the same authority as a supercluster weighing in at quadrillions of solar masses. That absence got its name in 2017, when Hoffman's team published their full findings in the journal Nature Astronomy. They called it the Epole Repeller, a name built to describe exactly what it does rather than what it looks like, because there was nothing there to look at in the first place. Its location fell almost perfectly opposite the Shapley concentration on the far side of the sky, from where all that mass was pulling from. Distance estimates place it somewhere between 700 and 740 million light-years away, sitting roughly along the same axis as Shapley, but facing the completely other direction. Shapley pulls from one side. The repeller, in whatever sense a void can be said to do anything, sits on the other. Here is the part that needs to be stated carefully, because it is easy to get wrong. Gravity does not repel. It never has, and nothing about this discovery changes that basic rule. What actually happens is subtler and, in its way, stranger. A region of space holding less mass than the average density around it creates an imbalance in the gravitational pull acting on anything nearby. The denser regions on every other side keep pulling, as they always have. The underdense region simply pulls back less. And when every other direction is tugging harder than the empty one, the net effect looks exactly like something pushing you away from the empty side, even though nothing is doing any pushing at all. Picture a crowded room where people are packed in on every side of you, each one close enough to nudge you slightly as the crowd shifts. Now, imagine a third of the people on one side of that room quietly leave. Nobody shoved you. Nobody pulled you deliberately in any direction. But the moment that one side thins out, the remaining crowd on the other sides tips your balance toward them, simply because their pressure is no longer being matched. You drift toward the fuller side of the room, and if you didn't know better, you'd swear something on the empty side had pushed you out. That is what the dipole repeller does to the local group, at a scale that spans hundreds of millions of light years, instead of a few feet of floor space. Hoffman's team found that this single mechanism accounts for something close to half of the Milky Way's entire peculiar velocity, not a minor correction tucked into the margins of the calculation. Half of the 600 plus kilometers per second econ the cosmic microwave background dipole first revealed decades earlier turns out to come not from something pulling us forward, but from something failing to hold us back. State that plainly and let it sit exactly as flat as it sounds. We are not simply falling toward Shapley and the Great Attractor. We are also fleeing an absence, drifting away from a stretch of the universe that never filled in the way its surroundings did. Half our motion through space is a response to something that isn't there. That finding rewired the entire model of how the local group moves. Attraction and repulsion, mass and its absence, working in tandem to produce one measured velocity. But even with that picture complete, the zone of avoidance had not finished handing over its secrets. There was still something sitting inside that obscured strip of sky that every prior survey, radio and infrared alike, had somehow managed to miss entirely. By the mid-2010s, most astronomers assumed the zone of avoidance had given up its major secrets. Norma had been found. The Great Attractor's true scale had been corrected. Shapley had been folded into the picture. The remaining gaps, everyone figured, were small ones, scattered galaxies too faint to matter much to the overall map. Renée Kran-Korteweg did not share that assumption. An astronomer who had spent much of her career specifically hunting for structure hidden behind the Milky Way's disk, she led a survey campaign in 2016 and 2017, using the Southern African Large Telescope, one of the largest single optical instruments in the Southern Hemisphere. Her team pushed deep into the reddened, dust-choked strip of sky that had frustrated observers since Proctor first noticed it was empty in 1878, gathering spectra from galaxies so faint and so obscured that earlier surveys had simply passed over them. What came back was not a scattering of minor objects. It was an entire supercluster, sitting roughly 800 million light-years away, comparable in total mass to Shapley itself. Astronomers named it the Vela supercluster, after the constellation it sits behind. Consider what that means. A structure carrying something on the order of tens of thousands of galaxies worth of mass. One of the largest concentrations of matter in this whole region of the universe had gone completely undetected through decades of increasingly sophisticated surveys. Not because nobody was looking, because it happened to sit almost exactly behind the thickest, most heavily obscured section of our own galactic disk, in a patch of sky that swallowed its light more completely than almost anywhere else astronomers had already searched. Early estimates of Vela's contribution to the Milky Way's total motion put the number at several dozen kilometers per second, a real but modest addition to the total velocity budget, and one still being refined as more of the structure comes into focus. It is not the dominant term in the equation. But it is not nothing either, and for decades it simply was not there in anyone's calculation at all. Call this the hidden mass budget, because that is exactly what it is: the persistent, recurring gap between what telescopes can directly confirm and what the observed motion of galaxies insists must exist somewhere nearby. Every time astronomers believed they had closed that gap, whether with Norma, with Shapley, with the dipole repeller's absence of mass, the ledger balanced for a while, then quietly opened again. Vela is simply the newest entry in a column that keeps refusing to stay closed. There is a pattern worth sitting with here, one that should unsettle anyone confident the map of our cosmic surroundings is finally finished. Norma was missed for decades. Shapley sat filed away as irrelevant for 50 years. Vela hid behind the dust through every major survey run before 2016. Each discovery came not because the universe grew more structure in the meantime, but because instruments finally became good enough to see what had been sitting there the entire time. And the instruments were about to get considerably better. A new radio array, built specifically to stare through the one obstacle that had defeated every prior generation of telescopes, was already coming online in South Africa, and it was about to make the hidden mass budget far harder for anyone to ignore. That new instrument is called Meerkat, an array of 64 radio dishes spread across the Karoo Desert in South Africa, all wired together to work as a single far larger telescope. Individually, each dish is unremarkable. Combined, pointed at the same patch of sky and processed as one instrument, they achieve a sensitivity no single radio telescope had reached before, and they turned that sensitivity directly on the one region of sky. The technique underneath Meerkat's survey work is the 21 centimeter hydrogen line, a specific radio wavelength emitted by neutral hydrogen atoms scattered through every galaxy in existence. Dust does not touch it. Starlight does not drown it out. A galaxy sitting behind the thickest, most obscured section of the Milky Way's disk broadcasts that same 21 centimeter signal as freely as one sitting in open, empty sky. The obstruction that had blinded optical astronomers for a century simply does not apply at this wavelength. Since 2017, that capability has been turned loose on the zone of avoidance in a sustained, ongoing survey, and the results have not slowed down. Hundreds of previously unknown galaxies have already been catalogued in the region. Structures that sat completely undetected through every prior generation of instruments revealed now, simply because something finally listened at the right wavelength. Researchers working on the survey are honest about how much remains. Current estimates suggest as many as 1,000 additional galaxies may still be hiding in the deepest, most heavily obscured pockets of dust, structures too faint or too buried for even Meerkat sensitivity to have caught yet. That is not a small margin of error. That is an acknowledgement that the map, even now, is incomplete by a meaningful fraction. Here is the pattern worth holding on to as this investigation continues. Every single survey of this region, going back to Proctor's zone of few nebulae in 1878, has found more structure than the survey before it expected. The infrared astronomical satellite found galaxies optical telescopes had missed. Early radio work found the Norma cluster. Krahn-Korteweg's team found an entire supercluster in Vela. And now, Meerkat, with better sensitivity than anything that came before it, keeps finding more. That should unsettle anyone confident that this particular map is finished. A region that has never once, in nearly 150 years of study, produced fewer surprises than the last survey, is not a region where you get to assume the accounting is closed. And that same unsettling pattern, more structure than expected, hiding just past the edge of what current instruments can confirm, was about to show up again. Not behind a wall of galactic dust this time, but at a scale so much larger that the obstruction blocking the view was not the Milky Way's disk at all. It was the observable universe itself. In 2008, a NASA astrophysicist named Alexander Kishlinsky published a claim that made a lot of his colleagues visibly uncomfortable. He was not looking at nearby galaxies anymore. He was looking at galaxy clusters spread across billions of light years, using something called the kinematic Sunyaev-Zeldovich effect, a subtle signature left behind when hot cluster gas moves relative to the cosmic microwave background and slightly distorts the ancient light passing through it. Measure that distortion across thousands of clusters, and in theory, you can map how those clusters are actually moving at distances no peculiar velocity survey had ever reached before. Kashlinsky ran that measurement across a large sample of clusters spanning a huge stretch of the observable universe. What came back was coherent motion. Thousands of clusters scattered across billions of light years, all drifting in roughly the same direction at a speed too consistent to write off as scatter in the data. He called it dark flow. Here is why that claim landed so hard. Everything discussed up to this point, the great attractor, Shapley, the dipole repeller, Vela, all of it involves structures sitting well within the observable universe. Structures that better telescopes could eventually locate and weigh. Dark flow implied something categorically different. If clusters billions of light years apart are all drifting the same direction with no visible structure nearby, massive enough to explain it, the source of that motion has to sit beyond our observable horizon, not hidden behind dust. Not too faint for current instruments, permanently, physically unobservable, because its light has not had time to reach us since the beginning of the universe, and never will. That is not a gap current telescopes might close with better sensitivity. That is a gap built into the structure of space and time itself. The Planck satellite was supposed to settle the question. Operating between 2013 and 2016, Planck mapped the cosmic microwave background with a level of precision no prior instrument had matched, and when its team searched for the same dark flow signature, they found nothing statistically significant. No coherent drift, no unexplained motion at the scale Kashlinsky had reported. Most of the astronomical community treated that null result as the end of the argument. Dark flow, in the consensus view, had been a false signal, likely the product of subtle systematic errors in the earlier cluster catalogue, rather than evidence of anything beyond the horizon. Kashlinsky did not accept that conclusion. He argued the Planck analysis had applied different assumptions and a different methodology than his original work, effectively testing a different question and calling it a refutation. He continued publishing, continued defending the original measurement, and the disagreement was never fully resolved in either direction. No new consensus formed, no follow-up study definitively closed the case on either side. Here is the honest position, stated plainly. Scientists disagree. dark flow remains a contested claim in the literature, neither confirmed nor cleanly disproven. Sitting in the uncomfortable space between a real detection and a statistical artifact nobody has managed to fully explain away. Whether Kashlinsky was right or wrong about clusters at the edge of the observable universe, an entirely separate anomaly was about to surface much closer to home, built from a far larger dataset than anything used in the dark flow debate, and it was about to reopen the exact same uncomfortable question: whether the universe at its largest scales actually looks the way cosmology has always assumed it should. That larger dataset arrived in 2023 under the name Cosmic Flows 4. The fourth, and by far the most ambitious version of the catalogue, Tully and Courtois had started building 2 decades earlier. Nearly 56,000 galaxy distance measurements went into it, an order of magnitude beyond anything used to first map Laniakea back in 2014. This was not a niche survey looking for one particular structure. It was an attempt to measure the true motion of the local universe at a scale and precision nobody had managed before. The finding that came out of it did not fit quietly into the existing model. At scales spanning roughly 500 to 650 million light-years, the same range where the Great Attractor and Shapley operate, the catalogue measured bulk flows, meaning the coordinated drift of entire populations of galaxies running between 380. Compare that to what standard cosmology actually predicts at those distances. The working model, built on decades of observation and tested against nearly everything else in modern astrophysics, expects bulk flow at that scale to sit closer to 140 kilometers per second decant. Cosmic Flows 4 measured motion roughly 3 times that number. A threefold discrepancy is not a rounding difference. It is not the kind of gap that gets explained away by slightly better calibration on the next pass. Run the statistics on how likely a result like that would be if the standard model was simply correct, and the answer comes out to something like 1 chance in 650,000. That is not marginal. That is the kind of number that gets a result taken seriously by people who spend their careers trying to prove such results wrong. Cosmology rests on one assumption more than any other. At the largest scales, the universe looks roughly the same in every direction. No preferred direction, no region secretly denser or faster moving than the rest once you zoom out far enough. Everything about how astronomers calculate expansion, map structure, and predict the motion of galaxies depends on that assumption holding. A bulk flow 3 times larger than predicted, at a confidence level this strong, is not a minor anomaly sitting comfortably inside that framework. It is a direct strain on the framework itself. The response from the field was not to dismiss the result outright. In 2026, a follow-up reanalysis went back through the Cosmic Flows 4 data using a prior-free approach, specifically checking whether uneven sky coverage in the original survey, more galaxies measured in some directions than others, might be inflating the apparent signal. That correction did reduce the size of the discrepancy. It did not eliminate it. A real, unexplained gap between observation and prediction remained even after accounting for the survey's blind spots. Here is the position cosmology finds itself holding right now, however uncomfortable it sits. The rule that the universe should look uniform at the largest scales is not something anyone has proven wrong. But it is a rule currently under real, measured strain, backed by the largest galaxy catalogue ever assembled, and no clean explanation has closed that gap yet. This first investigation, built entirely around invisible pulls and unexplained motion, ends here without full resolution. What comes next has no such ambiguity. sitting at the exact center of the galaxy, is something with a source you can point to directly, one that took 50 years and two competing teams on opposite continents to finally confirm. The year was 1931. A young engineer named Karl Jansky spent his days in a field outside Homdal, New Jersey, standing beside a strange contraption of pipes and wooden beams mounted on wheels salvaged from an old Model T. His job had nothing to do with galaxies. Bell Telephone Laboratories wanted to know what kept interrupting transatlantic phone calls, and Jansky's rotating antenna was built to hunt down the source: static, storms, anything electrical enough to explain the interference. Most of what he picked up matched storms on the horizon, exactly as expected. But one signal refused to behave like weather. It came back every single day, drifting slightly earlier by about 4 minutes with each rotation. The same shift you'd expect from something tracking the stars rather than the local sky. Jansky followed that pattern for months before he understood what it meant. The signal was not coming from Earth's atmosphere at all. It was coming from deep space, from the direction of the constellation Sagittarius, from somewhere near the center of the Milky Way itself. He published the finding in 1933. Almost nobody noticed. The astronomy of the era ran entirely on visible light, and the idea that the sky was quietly broadcasting in wavelengths no human eye could register struck most researchers as a curiosity, not a discovery worth chasing. It took an amateur to chase it. Grote Reber, a radio engineer with no formal astronomy training, built a dish antenna in his own backyard in Illinois, specifically to confirm what Jansky had found. Working alone through the late 1930 seconds, Reber mapped the signal's strength across the sky and located its peak with far more precision than Jansky's original instrument allowed. The brightest point sat dead center of the galaxy, in the exact direction of Sagittarius. Astronomers eventually gave that location a name: Sagittarius A. Here was the paradox nobody could resolve at the time. Whatever occupied that spot was pouring out enormous quantities of radio energy, more than any known star, more than any nebula catalogued up to that point. And when astronomers turned their best optical telescopes toward the exact same coordinates, they found nothing. No bright star, no visible glow, nothing to match the sheer power radiating out in wavelengths the human eye could never see. That contradiction sat unresolved for decades, quietly hardening into one of the central open questions of galactic astronomy. What kind of object screams that loudly in radio waves, while staying completely invisible in ordinary light? Answering it properly would take 50 more years better instruments than Jansky or Reber ever had access to. And eventually, two competing research teams working on opposite sides of the planet, racing toward the same impossible target at the center of everything. Proving what actually sat at that location required abandoning radio waves and turning to a different part of the spectrum entirely. Visible light could not get past the dust choking the galactic center, but infrared light could, slipping through the same cosmic haze that blocked every optical telescope pointed in that direction. Starting in the 1980 seconds, astronomers began using infrared cameras to track individual stars swarming around Sagittarius A, watching them move night after night, year after year, in a project that would eventually stretch across decades. What they found broke the intuition anyone would bring to the problem. Consider how a tetherball behaves. Give it a long rope and a gentle push, and it circles slowly, lazily, taking its time to swing around the pole. Shorten that rope, and the ball has to move dramatically faster just to stay in orbit, whipping around in a fraction of the time. The stars closest to Sagittarius A were behaving like a tetherball on an impossibly short rope, completing tight, fast loops that only made sense if something with tremendous mass sat at the center, holding them there. The shorter the orbit, the faster the star needed to move, and the stars nearest the core were moving fast enough to demand an anchor far heavier than anything visible. Two research teams took on the job of measuring exactly how heavy. Andrea Ghez led one group working out of the United States, building her stellar orbit data from telescopes in Hawaii. Reinhard Genzel led an independent team based in Germany, using different instruments, different calibration methods, and an entirely separate set of observations. Neither team was working off the other's numbers. They were racing on separate continents, tracking the same stars through the same dust, trying to beat each other to a confirmed answer. Their results converged almost exactly. Genzel's team clocked the central mass at roughly 4.15 million times the mass of the Sunday. Gez's team landed at close to 4.3 million solar masses. Two groups, two continents, two completely independent methods, arriving within a few percent of the same staggering number, all of it compressed into a region smaller than the solar system itself. That kind of agreement, reached without either team relying on the other's data, is about as close to certainty as astronomy gets. The two lead scientists shared the Nobel Prize in Physics in 2020 for the work, a recognition that closed nearly 90 years of uncertainty, stretching back to Jansky's rotating antenna in that New Jersey field. Here is the detail worth sitting with plainly. Nobody has ever photographed Sagittarius A directly, and nobody ever will. Not because instruments aren't good enough, but because a black hole by definition emits nothing to photograph. What Ghez and Genzel actually proved was an absence, a gravitational signature written into the motion of everything nearby rather than any image of the thing itself. You confirm a black hole exists the same way you'd confirm a whirlpool exists in murky water, not by seeing the drain, but by watching everything around it get pulled into the same tightening spiral. The mass was settled. The location was settled. What remained was a stranger problem entirely, because once astronomers turned their full attention to the stars actually orbiting that confirmed monster, what they found made no sense according to any model of how stars are supposed to form in the first place. Once Ghez and Genzel confirmed the mass sitting at the galactic center, their tracking data revealed something orbiting that black hole that should not exist at all. A tight cluster of stars, dozens of them, circling Sagittarius A*, at distances far closer than anything in our own solar system. Astronomers call it the S cluster, and every star inside it is young, massive, and blazing hot. The kind of star that typically takes shape inside a calm, undisturbed cloud of gas over hundreds of thousands of years. There is nothing calm about the region these stars occupy. A star forms when a cloud of gas grows dense enough and cold enough for gravity to pull it into a collapsing ball. Near a black hole weighing over 4 million solar masses, that process should be almost impossible. Tidal forces near the core stretch and shear any gas cloud long before it can hold together. Radiation pouring off the surrounding environment heats gas that needs to stay cold to collapse. By every standard model of star formation, the S cluster should be empty, a swept, sterilized zone where nothing new is ever born. And yet the stars are there, young by any stellar measure, orbiting close enough to complete a full loop around the black hole in a matter of years rather than millions. The leading explanation among astronomers is migration. Under this theory, these stars did not form where we find them now. A dense cluster of young stars formed much farther out in a colder, quieter pocket of gas where collapse was actually possible, then slowly spiraled inward over time, losing energy to the surrounding stellar traffic until it settled into the tight orbits observed today. The original cluster likely dispersed somewhere along that journey, scattering its members into the individual orbits astronomers now track one star at a time. One of those stars carries more data behind it than any other object this close to the black hole. Astronomers call it S2, and its orbit takes just 16 years to complete a full loop, a blink of an eye compared to how planets move around ordinary stars. At its closest approach, S2 reaches speeds near 3% the speed of light, fast enough that relativistic effects stop being a theoretical footnote and start showing up directly in the data. In 2018, during one of those closest approaches, astronomers measured something specific: a gravitational redshift in S2's light, a subtle stretching of its wavelength caused by the sheer strength of the gravity it was passing through. That measurement matched Einstein's general relativity prediction with remarkable precision, a direct confirmation of how gravity behaves in one of the most extreme environments accessible to observation anywhere in the galaxy. S2 behaved exactly the way the physics said it should. Not every object tracked near that black hole was willing to cooperate so cleanly. S2 confirmed Einstein's math and then went back to its orbit like nothing unusual had happened. 6 other objects near Sagittarius A** did something stranger. Astronomers started finding them in 2004, cataloging one after another over the following years, each one orbiting the black hole on a timescale ranging from 170 years to as long as one. They named them the G objects, and from the moment the first one showed up in the data, nobody could agree on what they actually were. They looked like gas. Stretched, glowing, diffuse at the edges. Exactly the kind of loose cloud you'd expect a black hole to tear apart on its first close pass. And that is precisely what should happen to a cloud like that. Picture a water balloon held between 2 hands, stretched farther and farther apart until the walls give out and the whole thing bursts into scattered droplets. Gravity near Sagittarius A** works the same way on anything without enough internal structure to resist it. The side of an object closer to the black hole gets pulled harder than the side farther away, and that difference in pull, called tidal force, stretches loose material until it comes apart entirely. A true gas cloud, passing that close, should not survive the encounter intact. One of these objects, G2, gave astronomers the chance to watch that process happen in real time. Its orbit brought it to closest approach in 2014, and telescopes around the world turned toward the galactic center months in advance, waiting for the show. The models were specific. G2 would stretch, shed material, and dump enough gas onto the black hole to trigger a bright, sustained flare, visible proof of a star-sized meal finally being swallowed. The flare never came. G2 stretched exactly as predicted on its way in, its shape smearing out along the orbit the way a true gas cloud should. Then, on the way back out, it did something a gas cloud cannot do. It pulled itself back together. The elongated shape contracted, tightened, and reformed into something close to its original compact structure, as if the closest pass to a supermassive black hole had barely left a mark. Gas alone does not do that. Something inside G2 was holding it together, some source of internal gravity strong enough to resist being torn apart by one of the most extreme tidal environments in the galaxy. The explanation astronomers now favor involves 2 stars, not one. A pair of stars locked in a tight binary orbit, drawn slowly closer together over time by the black hole's gravity, until they merged into a single swollen stellar body. That merger would release a thick shell of gas and dust around the newly combined star, an outer layer loose enough to behave like a cloud from a distance, glowing and diffuse, while a genuine stellar core sits hidden underneath it. Picture a hard-boiled egg wrapped in a thick layer of loose cotton. From the outside, all you see is soft material that gives easily under pressure. Pull on it, stretch it, and the cotton deforms exactly the way a gas cloud would. But at the center sits something solid enough to snap back into shape once the pulling stops. That explanation fits the data. It is still not confirmed. No telescope has managed to see past the gas envelope and image whatever stellar core might be sitting inside any of the 6G objects directly. The theory holds up. The proof remains out of reach. Whatever is happening to matter that close to the black hole, something else in that same crowded, violent stretch of space was quietly building a different kind of mystery, a boundary that nothing from farther out in the galaxy seemed able to cross at all. In 2020, data from the Fermi Large Area Telescope turned up something that had no business existing. Cosmic rays, the near-light speed particles that flood every corner of the galaxy, were simply not making it into the central molecular zone from outside. The count dropped off sharply right at the boundary, as if something invisible had drawn a line around the galactic core and posted a guard at every entrance. To understand why that matters, you need to understand what a cosmic ray actually is. These are not photons, not light of any kind. They are protons and atomic nuclei, stripped bare and flung across the galaxy at speeds pressing right up against the speed of light itself. In 1991, a detector in Utah caught one moving so fast that physicists nicknamed it the "Oh my God" particle, a single subatomic fragment carrying the kinetic energy of a thrown baseball. Cosmic rays like that are not gentle. They pass through gas clouds, through magnetic fields, through most of what the galaxy has to offer, largely unbothered, except, apparently, at the edge of the central molecular zone. Something there was stopping them cold, or at least stopping the ones trying to get in from outside. Particles born inside the zone seemed to leave just fine. It was the traffic heading inward that ran into a wall. Two competing explanations have emerged, and neither one has closed the case. The first points to magnetism. The region surrounding Sagittarius A** carries magnetic fields roughly 1,000 times stronger than the average found elsewhere in the galaxy. Under this theory, those fields compress at the boundary of the molecular zone into something like a magnetic curtain, dense and organized enough to deflect incoming charged particles before they ever reach the interior. Cosmic rays, being charged, follow field lines the way iron filings snap into place around a magnet. A strong enough wall of compressed field lines could, in principle, bend those particles away entirely, redirecting them around the zone rather than through it. The second explanation points outward instead of at structure. The galactic center is not a quiet place. Stellar winds, supernova remnants, and the general churn of activity near Sagittarius A** all push gas outward in a sustained current, a galactic wind strong enough to shake the surrounding environment on its own. Under this theory, that outflow acts less like a wall and more like a river running against the current, physically pushing back on any cosmic ray attempting to travel inward, the same way a strong headwind can stall a swimmer trying to cross against it. Both explanations fit pieces of the data. Neither one fully accounts for the sharpness of the cutoff Fermi detected, and researchers studying the region are honest that the true mechanism, whether magnetic, kinetic, or some combination nobody has modeled correctly yet, remains genuinely unresolved. Whatever is holding that barrier in place is clearly connected to the same restless environment, producing G2's stubborn survival and S2's precision orbit. And that same barrier, it turns out, is not the strangest thing coming out of that stretch of sky. Just beyond it sits a glow with no confirmed source at all, one that has kept two entirely different explanations alive for over a decade. That glow showed up in 2009 when the Fermi telescope caught something spreading out from the galactic core. In every direction at once, a smooth haze of gamma rays extending roughly 5,000 light-years from the center. No jets, no visible point source, just a soft, even glow filling the space around Sagittarius A Asteris, like light through frosted glass. What made the discovery serious rather than curious was the energy signature. The specific range of gamma-ray energies coming out of that glow matched a prediction physicist had written down decades earlier, long before Fermi ever launched, describing exactly what should happen if dark matter particles collided with each other and annihilated. That prediction had sat untested for years, a piece of theoretical bookkeeping waiting for an observation that might never come. Suddenly, there was a glow, sitting in almost the right place, carrying almost the right energy, doing almost exactly what the old models said dark matter annihilation should look like. Consider what confirmation would actually mean. Dark matter makes up roughly 85% of all matter in the universe, and in the better part of a century since its gravitational effects were first noticed, nobody has ever directly observed it doing anything. Every piece of evidence for its existence comes from what it does to things we can see: bent light, oddly fast galaxy rotations, gravitational pulls with no visible source. A signal like this would be different. It would be dark matter caught in the act, not inferred from its influence on something else, but observed directly, for the first time in the history of physics. That is an enormous claim, and enormous claims get picked apart before they get accepted. A competing explanation surfaced almost immediately, and it did not require any new physics at all. Pack roughly 100,000 faint millisecond pulsars into that same region near the core, each one too dim on its own for any telescope to resolve individually, and their combined light would blend into exactly the kind of smooth, uniform glow. No dark matter required, just an extremely dense population of ordinary, if exotic, dead stars, hiding in plain sight because there are simply too many of them packed too closely together to tell apart. Here is the problem nobody has managed to solve. Current telescopes cannot distinguish between these two explanations. A glow made of 100,000 overlapping pulsars looks, at this resolution, essentially identical to a glow made of annihilating dark matter particles. The data that would settle the question, individual pulsars resolved one at a time instead of blurred into a collective haze, sits just past the edge of what existing instruments can achieve. State the situation exactly as it stands, because it deserves to be stated without softening. Two explanations remain on the table. One of them, if confirmed, would represent the most significant direct detection in the history of dark matter research. The other would confirm nothing new at all, just an unusually dense population of known objects sitting where models already expected large numbers of old stars to accumulate. Both explanations are scientifically serious. Both fit the data collected so far. There is currently no way to choose between them. While that debate sits unresolved, a different signal turned up from somewhere inside that same crowded stretch of sky, smaller, stranger, and matching no known category of object at all. In 2021, The mere KT array turned up a radio signal that fit into no existing file. Researchers working the survey nicknamed it Andes object, a casual name for something that has resisted every attempt to explain it since. The first clue sat in how the signal was polarized. Radio waves coming off most astronomical sources arrive, scrambled, oscillating in every direction at once. Andes object did not do that. Its waves lined up, locked into a consistent orientation, the signature of a magnetic field strong enough and organized enough to force radiation into a single coherent pattern before it ever left the source. That kind of extreme polarization does not happen by accident. Whatever produced it sits inside one of the more powerful, tightly structured magnetic environments astronomers have measured anywhere near the galactic core. There is a second layer buried in that same polarization, something called Faraday rotation. As polarized light travels through charged gas, the magnetic field threading that gas twists the angle of polarization bit by bit, and the amount of twisting tells you something about the density and strength of everything the signal passed through on its way to the detector. Reading the Faraday rotation on Andes object gave astronomers a rough map of the magnetic weather it had traveled through, confirming again that this was a source embedded in a genuinely extreme corner of the galactic center, not simply a distant echo passing through calm space. None of that would be especially strange on its own. Plenty of objects near Sagittarius A** sit inside powerful magnetic fields. What sets Andes object apart is timing. The signal switches on for stretches lasting weeks to months, then goes silent for irregular periods that follow no discernible pattern. Pulsars blink on a strict, predictable clock. Magnetars flare and fade according to known decay processes. Fast radio bursts, whatever their true nature, tend to repeat on identifiable cycles once enough data accumulates. Andes object does none of that. Its active phases arrive without warning and end without explanation, and nothing in the existing catalogue of galactic objects behaves quite this way. Astronomers have run it against every known category. Pulsar rotation does not fit. Magnetar outburst behavior does not fit cleanly either. Transient flare models built for other known sources fail to reproduce the specific rhythm or lack of rhythm that Meerkat keeps recording. Here is where the honest scientific position has to stay honest. The signal is real. The polarization measurement is solid. The irregular timing has been confirmed across multiple observing runs, not a single fluke reading. What remains completely open is the cause. Andes object may turn out to be a known type of object, behaving in some unusual configuration nobody has modeled yet. It may also represent something genuinely new, an entire class of source that has simply never been catalogued before now. That kind of open question, sitting unresolved this close to a confirmed supermassive black hole, raises something larger than just one strange signal. It starts to ask whether the black hole itself, as confirmed and precisely measured as it is, tells the complete story of what actually occupies the center of this galaxy. Every measurement discussed so far assumes one thing without questioning it, that a black hole, specifically, sits at the center of the galaxy. A small group of researchers has asked, what happens if that assumption is wrong? Not wrong about the mass, wrong about the form that mass takes. The alternative they propose is a dark matter core, a densely packed concentration of dark matter sitting at the galactic center instead of a true dark matter clumps under gravity, same as ordinary matter does. And in theory, given enough time and the right conditions, It could compress into something dense enough to produce the exact same gravitational pull astronomers have measured coming from Sagittarius A*. Same mass, same influence on nearby orbits, different physical object entirely. Here is why this idea does not collapse immediately under scrutiny. Most of the stars used to measure the central mass, the wide, slow orbits filling out that early data, sit far enough out that a black hole and a sufficiently dense dark matter core would tug on them identically. Gravity does not announce what it is made of. At those distances, the two models are functionally indistinguishable, and decades of stellar tracking simply could not tell them apart. What did settle the question, or came close to settling it, arrived in 2022. The Event Horizon Telescope released its image of Sagittarius A*, a glowing ring wrapped around a dark central shadow. That shadow's size and shape matched general relativity's prediction for a true black hole event horizon with striking precision. A dark matter core does not produce a shadow like that. It has no event horizon to cast one. The image stands as the strongest direct evidence that whatever sits at the center is an actual black hole, not a disguised concentration of invisible particles. That should have closed the case entirely. It did not, quite. A handful of stars tracked closest to the core, the same tight orbits that gave us S2's relativistic redshift, show small deviations that a single, isolated black hole does not fully explain on its own. Tiny wobbles in trajectory, subtle departures from the orbit a lone point mass should produce, not large enough to reopen the dark matter core debate outright, but large enough that astronomers have had to propose something extra, sitting alongside the black hole rather than in place of it. Two live candidates remain on the table. One is a population of intermediate mass black holes, smaller companions orbiting close enough to Sagittarius A* to tug on nearby stars without being individually resolved. The other is a diffuse component of dark matter, not concentrated enough to replace the black hole entirely, but present enough nearby to add a small, measurable distortion to the orbits closest to the core. Whatever occupies that space, the black hole, is real. The shadow confirmed that much directly. But something else appears to be riding along with it, and untangling exactly what that something is remains unfinished work. What the black hole has already done long before any of these current measurements existed turns out to tell a far stranger story than anything happening there right now. The black hole tells a stranger story about its past than its present, and that story is written directly onto the sky in a shape too large to miss once you know to look for it. Astronomers found it in 2010 using the same Fermi Large Area Telescope that later caught the cosmic ray barrier and the gamma ray excess near the core. Two enormous lobes of gamma ray and microwave emission balloon out from the galactic center, one above the disk of the Milky Way, one below it, mirror images of each other spanning roughly 50,000 light-years combined. Astronomers name them the Fermi bubbles, and their edges are sharp enough, their shape symmetrical enough that they read less like a slow accumulation of scattered energy and more like the aftermath of something specific. Two competing explanations account for where that energy came from, and they mirror the same tension that has followed nearly every mystery near this black hole. One explanation points to Sagittarius A* itself, proposing a past phase of active jets, a period when the black hole was feeding aggressively enough to launch focused streams of superheated material straight out along its poles, carving the bubbles into shape over a relatively short span of time. The competing explanation removes the black hole from the story almost entirely, crediting the bubbles instead to a buildup of energy from dense clusters of massive stars near the core. their winds and supernovae accumulating over a much longer stretch, slowly inflating the same structure without any single dramatic trigger. A separate line of evidence adds a second data point. This one measured in years rather than millions of years. Certain gas clouds near the galactic center, Sagittarius B2 among them, show something astronomers call an X-ray light echo, delayed reflection of radiation that bounced off the cloud after leaving the black hole's immediate surroundings. Reading that echo backward, astronomers calculated that Sagittarius A* was, within the past few hundred years, millions of times brighter in X-rays than it is today. Picture a whisper in an empty room that suddenly briefly becomes a scream, one loud enough that its echo is still bouncing off the walls centuries after the room went quiet again. That is roughly what these clouds are showing us, radiation reflecting a flare that already ended, arriving at our instruments only now because of how long light takes to cross that distance and bounce back. None of this describes a black hole locked permanently into silence. Current monitoring shows Sagittarius A* still flares in X-rays multiple times a day, brief spikes riding on top of its usual quiet baseline, and occasionally something larger, a sharp brightening tied to a clump of infalling gas finally crossing the point of no return. A black hole that has erupted before, echoes still fading through nearby clouds, and continues flaring on a daily basis in the present, is not a settled question. It is an open one. And that same restlessness inside our own galaxy sits alongside a far larger, far slower collision already in motion, one involving not a single object crossing the event horizon, but two entire galaxies bearing down on each other directly. Step back from the black hole entirely because something bigger has been closing in the whole time. Everything covered so far, the invisible pulls dragging the galaxy through space, the quiet monster at its center, has stayed contained within the boundaries of a single galaxy. That boundary is about to disappear. Roughly 2.5 million light-years away sits another spiral, roughly the same size as ours, closing that distance at approximately 110 kilometers per second econt. And it has been closing that distance for longer than complex life has existed on Earth. Andromeda. For over a decade, textbooks, planetarium shows, and popular science coverage have described what happens next in the same flat, certain language. Two galaxies on a direct collision course, no way out. The word used most often was inevitable, and inevitable is a strong word to apply to anything happening across a distance measured in millions of light years. That certainty is the thing about to get dismantled here, not the collision itself, the certainty surrounding it. Because the newest analysis of Andromeda's motion, built on data nobody had access to even 5 years ago, does not confirm the old story. It complicates it in ways that should unsettle anyone who assumed this particular ending was locked in stone. The galaxies are still approaching each other. That part has not changed. What has changed is how confident anyone can be about what approaching actually leads to, and when and whether it leads anywhere at all within a time frame that matters. The version most people have heard runs like this. Andromeda and the Milky Way make first close approach around 4 billion years from now, followed by a slow gravitational tangle that resolves into a full merger somewhere around the 6 billion year mark. That prediction came out of Hubble Space Telescope proper motion measurements, tracking Andromeda's stars across years of observation to work out not just how fast it approaches, but which direction it drifts sideways relative to us. For over a decade, that number held steady in the scientific literature and in every popular retelling that followed it. Sideways motion turns out to be the detail that mattered most, and it is also the detail that was hardest to pin down. A galaxy approaching us head-on collides. A galaxy approaching us at an angle might miss entirely, swinging past at a distance too great for gravity to pull it back in on any timescale worth discussing. Getting that angle wrong by even a small margin changes the outcome from certain collision to a near miss stretched out over billions of years. Dated analysis, combining Hubble data with newer measurements from the Gaia satellite, went back and reworked that sideways motion with far greater precision than the original Hubble estimate allowed. What came out of it was not a tighter number, it was a wider one. The uncertainty in Andromeda's transverse velocity turned out to be considerably larger than anyone had accounted for, large enough that the confident, direct hit trajectory from the earlier prediction was no longer the only plausible outcome or even necessarily the most likely one. Run that updated uncertainty through the models, and the numbers shift substantially. Instead of a near-certain collision, the revised probability of any collision at all within the next 10 billion years comes out to roughly 50%. A coin flip, mathematically, on whether these two galaxies ever meet within a span of time 10 times longer than the original prediction even required. It gets more dramatic than that once you stop treating this as a two-body problem. The Milky Way and Andromeda are not alone out here. Factor in the gravitational influence of the Large Magellanic Cloud and the Triangulum Galaxy, both of which tug on the larger orbits in ways the simpler earlier models left out entirely, and the odds shift again. The probability of a head-on collision, specifically within that original 4 to 5 billion year window, drops to somewhere around 2%. 2%. Sit with the size of that shift. For over a decade, the collision between these two galaxies was presented as one of the most certain long-term predictions in all of astronomy. The kind of fact repeated in documentaries and textbooks with the same confidence. The newest data does not say that prediction was wrong exactly. It says the confidence behind it was never as solid as the certainty in the telling implied. And once the actual uncertainty gets modeled honestly, this collision might not happen at all within any span of time that means anything to the story being told here. None of this cancels the possibility. A coin flip is still a 50% chance, not a 0% chance. And there remains a real, non-trivial pathway by which these two galaxies do collide, merge, and reshape each other completely. What changes is the tone. This is no longer a fixed appointment on the calendar of the universe. It is a probability competing against an equally plausible future, where Andromeda simply slides past, pulled along its own gravitational tangent, and the Milky Way keeps its spiral shape for a great deal longer than anyone expected. If that collision does happen, though, astronomers have modeled what follows in far greater detail than the arrival date itself. Picture two handfuls of sand thrown at each other from across a room. The clouds pass through one another completely, mixing, swirling, overlapping in the air, and yet, if you tracked every individual grain, almost none of them would actually touch. That is what a galaxy collision looks like at the level of individual stars. The Milky Way holds roughly 200 billion stars. Andromeda holds more. Space between them is so vast that even during the most violent phase of a merger, the odds of any two stars actually colliding remain close to zero. Distances between stars measure in trillions of miles. A star is a small target in an enormous room, and two galaxies can pass through each other almost entirely without contact at the stellar level. That does not mean nothing collides. The first close passage, whenever and if it happens, does not look gentle from a distance. Gravitational shear rips at both galaxies simultaneously, pulling long streams of stars out into tidal tails, stretching hundreds of thousands of light years. thin, glowing arcs flung outward like ribbons caught in a strong wind. The tight spiral structure both galaxies currently hold, the neat arms visible in any photograph of a spiral galaxy, gets shredded during this pass, torn out of alignment by forces neither galaxy's own gravity can resist. What does collide directly and violently? Gas. Unlike stars, gas clouds are not small, isolated points scattered across enormous distances. They are vast, diffuse structures that fill huge volumes of space. And when two galaxies pass through each other, their gas clouds slam together at extreme velocity. That collision compresses gas that had been sitting relatively calm for billions of years, and compression like that triggers sudden dramatic bursts of new star formation, entire regions of both galaxies lighting up with young stars in a firestorm. This does not happen in one clean pass and finish. Galaxy mergers unfold across repeated encounters, not a single impact. The two galaxies swing past each other. Gravity slows their outward momentum, and they get pulled back together for another pass, then another, each encounter draining a little more orbital energy from the system through a process called dynamical friction. Over the span of that process, spread across roughly 2 billion years once the first close approach begins, the two galaxies swing apart and crash back together multiple times before finally settling into one combined structure. What eventually remains bears no resemblance to either. Original galaxy, the spiral disks, the organized rotation, the clean arms winding outward from a central bulge. All of it gets erased in the churn of repeated passes. Stars that once moved in orderly, disconfined orbits end up scattered into a roughly spherical distribution, moving in essentially random directions rather than a shared rotational plane. The result is a single elliptical galaxy, sometimes nicknamed Milkomeda in the literature and in popular coverage. A smooth, structureless ball of stars replacing two once distinct spirals. No arms, no disk. Nothing that would look familiar to anyone comparing it to either galaxy as it exists today. That transformation is abstract until you make it personal. Somewhere inside that churn of repeated passes, tidal tails, and eventual flattening into an elliptical remnant, sits a modest yellow star, roughly 2/3 of the way out from the center of one of these two spirals, carrying with it a small rocky planet currently reading these words back to itself. What happens to that star and that planet during a process violent enough to erase two galaxies' worth of structure is a considerably more specific question than what happens to the galaxy as a whole. Simulation studies that track the Sun's position through a full galactic merger have narrowed the outcome down to a set of hard probabilities, and none of them involve destruction. The most likely single outcome, sitting at roughly 50% probability, places the Sun about 3 times farther from the new galactic center than it currently sits. Not thrown clear of the galaxy, relocated, dragged outward by the same tidal churn that shreds the spiral arms, dropped into a wider, quieter orbit around whatever elliptical remnant forms once the dust settles. The second outcome carries less probability, but far more drama. Roughly 12% of modeled scenarios end with the Sun ejected entirely, flung clean out of the merged galaxy and into the empty dark of intergalactic space. 12% is not a fringe result. Run that number enough times and it happens with real regularity. A star and its planets cut loose from the galaxy that built them, drifting alone through a void with no other galaxy close enough to call home. Here is what stays fixed no matter which of these outcomes plays out. The Sun does not lose its planets. Whether it ends up 3 times farther from a new galactic core or sailing through open intergalactic space with nothing else around it for millions of light years, the gravitational bond between the Sun and everything orbiting it remains intact. Earth stays exactly where it has always been relative to the Sun. Mercury, Venus, Mars, the outer giant, all of it continues orbiting undisturbed, indifferent to whatever chaos is reshaping the galaxy around the entire system. The merger scrambles a galaxy structure. It does not touch the architecture of a single solar system caught inside it. There is a timing detail worth sitting with directly, because it changes what this entire collision actually means for Earth. The Sun's own internal evolution, its slow brightening as it ages, its eventual expansion into a swollen red giant, is set to end Earth's habitability somewhere on the order of 1 billion years before Andromeda ever arrives close enough to matter. The oceans boil away, the atmosphere thins and cooks off. All of that happens on a schedule set entirely by the Sun's own internal physics, running independently of anything happening between the Milky Way and its neighboring galaxy. Humanity built its entire framework of time, its calendars, its sense of a stable overhead sky around a galaxy assumed to be a fixed backdrop. That backdrop turns out to be temporary, and the collision destined to eventually erase this galaxy's shape. One event popular science has spent over a decade treating as the defining ending of our cosmic story will not even be the reason Earth stops being habitable. Something quieter, already running on its own clock inside the Sun itself, gets there first. But the Sun and its planets, not the only structures caught up in what a full galactic merger leaves behind. Once two spirals become one elliptical remnant, the two black holes each galaxy carried at its center still have an entire final act left to perform. Two spirals become one elliptical remnant, and somewhere inside that new structure, two supermassive black holes are still sitting exactly where their host galaxies left them. Sagittarius A* survives the merger. Andromeda's central black hole survives it too. Neither one gets destroyed in the process. Instead, they end up drifting toward each other inside the same merged galaxy, drawn together by the same gravity that pulled the two galaxies into one shape in the first place, until they settle into orbit around a shared center of mass. Binary pair, two black holes locked together, sitting at the heart of whatever elliptical remnant the collision leaves behind. That binary does not stay wide forever. The same mechanism that dragged the two galaxies together over repeated passes keeps working on a smaller scale here too. As the black hole pair moves through the dense stellar population surrounding it, close encounters with individual stars siphon off small amounts of orbital energy with every pass. Each interaction is tiny on its own, a slight tug, a slight loss, barely worth noticing in isolation. Repeated over millions of years across an entire stellar population, that steady drain shrinks the binary's orbit bit by bit, pulling the two black holes closer together the same way friction slows anything moving through a resistant medium. Except here, the resistance comes from gravity itself rather than any physical substance. Modeling that process to its conclusion gives a surprisingly tight number. Once the full galactic merger completes and the binary settles into place, coalescence, the final moment where the two black holes actually merge into one, arrives within roughly 16 to 17 million years afterward. Compared to the multi-billion-year timeline required to bring two entire galaxies together, that is fast. The hard part, dragging two galaxies across millions of light years and grinding them into a single structure, takes billions of years. The last step, closing the final gap between two black holes already sitting in the same galactic core, takes a sliver of that time by comparison. The moment those two black holes finally merge, they do not do it quietly. That collision releases a burst of gravitational waves, ripples in space-time, carrying an enormous amount of energy outward in every direction, concentrated at frequencies too low for current ground-based detectors to catch. Space-based observatories currently in development are being built specifically with signals like this in mind, tuned to detect exactly this kind of low-frequency burst from similar mergers happening in galaxies scattered across the observable universe. Nobody alive will be here to record the specific signal this particular merger produces. But somewhere else, right now, a comparable merger between two other galaxies is likely playing out the same sequence, and the instruments built to catch it are already under construction. That merger closes one long-running story. Two galaxies became one. Two black holes became one. But everything covered up to this point, the invisible pulls, the awakening core, the eventual collision, shares one thing in common. Each involves something happening to the Milky Way. What comes next involves something happening inside it, on a much slower clock, with no external cause required at all. Step away from collision physics entirely, because the next threat facing this galaxy does not involve another galaxy at all. No incoming spiral, no black hole with a violent past, nothing crossing 2.5 million light-years to arrive here. This threat is already inside the Milky Way, running quietly in the background of every star that has ever formed here. And it has been running that way for billions of years. Here is the problem, stated as plainly as it can be stated. New stars require cold gas. That is the raw material, the fuel that collapses under its own gravity and eventually ignites into something burning bright enough to call a star. The Milky Way has a finite supply of that fuel, and it is being used up faster than the galaxy can replace it. Every star born inside these spiral arms draws down a reservoir that does not refill at the same rate it drains. There is something almost unsettling about how ordinary this threat is compared to everything else in this investigation. It requires no incoming galaxy, no eruption from the core, no exotic object lurking behind a wall of dust. It requires nothing except time and the simple accounting of a fuel supply running in one direction. A collision needs two galaxies on a converging path. Flare needs gas falling past an event horizon. This needs none of that. It is already happening, at this moment, inside every gas cloud in the galaxy, slowly cooling, collapsing, and being spent. Understanding exactly how serious that depletion is starts with understanding how a galaxy stays fed in the first place. What keeps that reservoir topped up, and what has been quietly tipping the balance the other way for longer than most of the galaxy's stars have existed. A galaxy stays fed the same way any system with a fixed budget stays solvent, by balancing what comes in against what goes out. On the income side sits inflow, gas pulled down from the halo surrounding the galaxy and from the thin intergalactic medium beyond it, drifting inward under gravity and eventually cooling enough to join the reservoir available for making stars. On the expense side sits outflow, gas driven back out by the very stars that reservoir produces. Pushed away in galactic winds powered by supernovae detonating and young massive stars blasting out radiation. Every star that ignites eventually gives some of that fuel back in a more violent form, and a portion of what gets given back leaves the galaxy entirely, rather than settling back down to be reused. Right now, the Milky Way holds roughly 10 billion solar masses of gas, cold and dense enough to eventually form stars. That sounds like an enormous number until you measure it against consumption. Divide that reservoir by the current rate stars are being born, and the math gives a depletion timescale of somewhere between 5 and 10 billion years. Not a hard deadline. A budget running down at a pace that can be calculated, with no restocking event currently large enough to reverse the trend. That puts the Milky Way into a specific category astronomers use to sort galaxies by where they sit in this process. Picture galaxies as falling somewhere along a spectrum, one end still blazing with active star formation, the other end fully quenched and dormant, its reservoir emptied out with nothing left to burn. The Milky Way sits in what gets called the Green Valley, caught in the middle of that spectrum, not dead yet, but no longer at the peak of its productive years either. It is a galaxy in transition, still forming stars, but forming them at a fraction of the rate it once did. That decline did not start recently. Chemical signatures locked into the ages and compositions of stars scattered throughout the disk show that star formation ran significantly higher billions of years ago than it does today, back before the galaxy's disk had even finished settling into the flattened structure it holds now. Once that disk formed, the rate of new star birth dropped, and it has continued dropping since, a slow, steady decline running in the background of everything else happening inside this galaxy. Here is where the simple picture gets complicated. Recent surveys looking closely at how this decline actually plays out across the galaxy have found that it is not uniform, not a smooth, even fade happening at the same pace everywhere at once. Some regions are running out of fuel faster than others, and in the middle of the most chaotic, gas-starved environment in the entire galaxy, researchers found something that should not have been there at all. The galactic center is not a gentle place. Radiation floods the region. Gravitational shear from the central black hole stretches and tears at anything drifting too close. Turbulence churns the gas into a constant boil, hot and violent enough that most models expect nothing calm to survive there for long. And yet, tucked inside that chaos, astronomers found a cloud of gas sitting quiet, cool, dense enough to hold together. The kind of cloud that anywhere else in the galaxy would already be well on its way to collapsing into new stars. Finding that pocket of calm in the most hostile environment the Milky Way has to offer matters more than it might first appear. It is proof, sitting right there in the data, that a galaxy sliding toward dormancy has not shut every door on new star formation. Even with the overall reservoir draining, even with the surrounding region hot enough and violent enough to prevent most collapse, conditions can still align in isolated pockets. The decline is real. It is just not absolute, and it is not uniform down to the smallest scale. That single discovery forces a harder question. If star formation can still happen in the worst possible neighborhood inside the galaxy, what exactly determines when it finally stops everywhere else? Broader studies of galaxies further along this same path than the Milky Way point to competing answers, and none of them has won outright. One explanation keeps it simple. Gas runs out, plainly and directly, and once the reservoir empties, nothing is left to collapse. A second explanation looks instead at structure, arguing that changes to a galaxy's shape, a growing central bulge, a stabilizing disk, can lock gas in place, prevent it from collapsing, even while plenty of raw material still remains. A third explanation points to feedback, energy pouring out from young stars, supernovae, and activity near the core, heating the surrounding gas until it simply gets too hot to condense into anything new, fuel or no fuel. These are not small disagreements. Gas depletion says the problem is supply. Structural stabilization says the problem is geometry. Feedback heating says the problem is temperature. Current research treats all three as active contributors, working in some combination that differs from one galaxy to the next, and nobody has produced a clean single answer for exactly how much weight each one carries inside the Milky Way specifically. What the best current modeling does offer is a number. Galaxies similar to the Milky Way, sitting in that same green valley category, caught between active formation and full dormancy, typically see star formation extinguished within roughly 5 billion years. That estimate already accounts for the temporary burst of new stars, expected once the Andromeda collision compresses gas clouds and briefly reignites formation across both merging galaxies. Even with that boost factored in, the long-term trend still runs the same direction. Down, knowing when the lights start going out is one thing. Knowing what the galaxy actually looks like once they do is a separate question entirely. And for that, the clearest answers come from galaxies that have already finished the process. The Milky Way is only partway through. Astronomers already have that answer sitting in their catalogs, because galaxies further along this same road exist by the thousands across the observable universe. They call them quenched ellipticals, and they represent the finished version of the exact process now unfolding inside the Milky Way. No spiral arms, no disk. Just a smooth, rounded mass of stars dominated almost entirely by old low-mass suns burning red rather than blue. That color shift is not a coincidence of aging. It is a direct consequence of which stars survive and which do not. Massive, blue-hot stars burn through their fuel fast, lighting up brilliant and dying within a few million years, a blink of an eye set against the galaxy's total lifespan. Once a galaxy stops manufacturing new ones, those blue giants disappear from the population first, one supernova at a time, and nothing replaces them. What remains behind are the stars built to last, the red dwarfs and aging red giants that sip their fuel slowly enough to keep burning for tens of billions of years. Strip away the blue, leave only the red, and the entire galaxy's light shifts color, dimming and reddening as its brightest, most short-lived residents burn out one by one. This is not a distant speculative endpoint. Galaxies reaching this stage have already been observed across cosmic history, and the timeline is sobering. Roughly half of all massive galaxies in the early universe had already been quenched, their star formation extinguished, by the time the universe itself was only 3 billion years old. Out of a universe now nearly 14 billion years old, that means a huge fraction of galaxies finished this transition before most of cosmic time had even played out. The Milky Way is simply arriving at the same destination on a longer, later schedule. Picture what that means for this galaxy specifically. Strip away the spiral arms entirely, along with every bright blue star-forming region currently visible from any dark sky on Earth. What remains is a smooth, featureless, reddish ball of ancient starlight, its gas reservoir reduced to little more than a thin hot halo, too diffuse and too heated to ever condense into anything new again. No structure worth naming. No bright nurseries lighting up the disk. Just a quiet, aging mass of stars, slowly fading toward a uniform dim glow that will hold roughly the same shape for the rest of time. None of this ends life immediately, wherever life happens to exist inside that fading structure, but it rewrites the terms every surviving system has to live under. The question stops being about what new opportunities the galaxy might still produce, and becomes entirely about what can be sustained using only what already exists. That question has a direct answer, and it starts with chemistry rather than astronomy. Every heavy element in your body, the calcium in your bones, the iron in your blood, was forged inside a star that lived and died long before the sun ever ignited. Planet formation depends on that same inheritance. A young star surrounded by a disk of gas and dust needs enough heavy elements already mixed into that disk to build something rocky, something with an iron core and a solid surface, rather than just another ball of hydrogen and helium. Fewer new stars being born means fewer new deposits of those heavy elements getting seeded into the galaxy going forward. The raw ingredient list for a rocky, Earth-like planet does not run out overnight, but the rate at which new opportunities for one to form keeps shrinking alongside the birth rate of the stars that would host it. There is a quieter upside buried inside this same decline. Massive stars are the ones that end their lives violently, as supernovae blasting radiation and high-energy particles across enormous distances, or in rarer cases as gamma-ray bursts capable of stripping the atmosphere off a planet several thousand light-years away. Massive stars are also the shortest-lived, the first casualties of a galaxy running low on the fuel needed to keep manufacturing them. As their numbers fall, so does the frequency of the catastrophic events they cause. A galaxy running out of new star formation is, in a narrow sense, a galaxy growing gentler, its most violent astrophysical hazards fading out along with its most massive residents. None of this threatens whatever life already exists on worlds already formed, at least not on any near-term clock. Red dwarfs, the small, dim, endlessly patient stars that make up the overwhelming majority of the galaxy's stellar population, do not burn out quickly. Some will keep fusing hydrogen for tens of billions of years. Others run the numbers to their theoretical limit, could still be burning hundreds of billions of years from now, long after every blue giant in the galaxy has gone dark, and long after the galaxy itself has finished its transformation into a quiet, reddened. Whatever already orbits those stars gets to keep going, different to the fact that nothing new is being built anywhere else. Here is the rule this settles into. A universe still busy manufacturing new stars is a universe still generating new chances, new planets, new possible cradles for something to begin. A universe that has stopped making them does not erase what already exists. It just closes the door on anything not already underway. Life, if it persists into that later era, persists entirely on inheritance. Nothing new arrives to replace it. That decline running through the galaxy's interior is only one half of what the Milky Way is facing. While the fuel for new stars keeps draining from the inside, something else is happening on a scale far larger than any single galaxy. Cutting this entire structure off from everything that surrounds it. There is one more scale shift left in this investigation, and it is the largest one yet. Everything up to this point has stayed inside the Milky Way's own boundary. Its motion through space, its restless core, its collision course with a neighboring spiral, its slow internal fade toward a quiet red future. What comes next steps outside that boundary entirely. This is not a story about a galaxy dying from within. It is a story about an entire cosmic neighborhood being cut off permanently from everything beyond it. State the mechanism plainly, because it is not complicated, even though its consequences are almost impossible to hold in your head. Dark energy is accelerating the expansion of the universe. Every year, more space opens up between galaxies that are not gravitationally bound to each other, and that stretching does not slow down as time passes. It speeds up. Structures far enough away, unbound to anything nearby, get carried farther and farther beyond reach, dragged along by the expansion of space itself, rather than any motion of their own. Here is the paradox, sitting at the center of everything left to cover. Gravity wins on small scales. It always has. The Milky Way, Andromeda, and the smaller galaxies gravitationally tied to both of them will keep pulling together regardless of what the wider universe is doing, merging, settling, forming one bound structure that holds together indefinitely. But zoom out past that local neighborhood, and the opposite rule takes over completely. Expansion wins everywhere else. Every galaxy not bound tightly enough to resist it will eventually recede beyond any possibility of contact, beyond any possibility of even being seen. Both of those outcomes are happening at the same time right now in the same universe. Close in, gravity is winning. Farther out, expansion already has the upper hand and is only tightening its grip. The Milky Way sits at the boundary between those two outcomes, gathering everything nearby into one final structure, while the rest of the observable universe quietly drifts away in every direction at once. Understanding how that split plays out starts with understanding exactly what holds the near side of that boundary together. Before getting to what is being lost, it helps to know precisely what is being kept. The local group is a name given to the collection of galaxies gravitationally bound together across a few megaparsecs of space, and depending on how thoroughly you count the smallest, faintest dwarf galaxies scattered around its edges, membership runs somewhere between roughly 70 and over 100 individual galaxies. Most of those are small, dim, and unremarkable on their own. Two are not. The Milky Way and Andromeda dominate this entire structure, each one carrying the overwhelming majority of the group's total mass, with everything else orbiting in their combined gravitational shadow. Add up every galaxy inside that boundary, every star, every cloud of gas, every halo of dark matter wrapped around each member, and the total comes to somewhere between roughly 2 and 5 times 10 to the 12th power solar masses. That is an enormous figure, but the important part is not the size. It is the fact that this entire mass, spread across dozens of galaxies and several million light-years of space, stays bound together as one coherent system, despite living inside a universe that is expanding in every direction. That is worth pausing on directly, because it sounds like a contradiction. The universe is stretching apart. The local group is not stretching apart. Both statements are true simultaneously, and the reason comes down to a simple contest of scale. Cosmic expansion adds distance gradually, a small stretching effect, accumulating across enormous spans of space. Gravity, at close range, is strong enough to overwhelm that gradual stretching completely. Inside a few megaparsecs, with this much mass concentrated, this closely together, gravity does not just compete with expansion. It dominates it outright, the same way it dominates within the Milky Way itself, holding stars in orbit, despite the same expansion technically acting on every point in space between them. Given that dominance, the long-term outcome for the local group is not really in question the way Andromeda's collision timeline turned out to be. The Milky Way and Andromeda merge, as covered already, into a single elliptical remnant. What happens after that merger completes is a slower, quieter continuation of the same process. The smaller satellite galaxies still orbiting within the local group, the dwarf galaxies too faint to notice from Earth without a serious telescope, do not escape this gravitational pull either. Over time, that same merged remnant absorbs them one by one, drawing each smaller system inward until essentially everything gravitationally bound to this neighborhood has been folded into one final structure. The end state, then, is not multiple galaxies loosely orbiting a shared center. It is one single object built from what used to be dozens of separate galaxies, holding together indefinitely because nothing left inside that boundary has enough independent momentum to escape it. Whatever else happens to the wider universe, this particular collection of matter stays intact. That permanence, though, is exactly what makes everything sitting just beyond the local group's edge so unsettling. While this internal merger runs its slow, inevitable course, something outside that boundary is already disappearing, not gradually joining anything, not folding into any larger structure, but simply receding, quietly and permanently, into a distance no future observer will ever be able to close again. The proof that the wider universe is slipping away arrived in 1998, and it arrived as a direct contradiction of what every physicist alive expected to find. Two independent teams were tracking distant supernovae, using the reliable, consistent brightness of a specific type of stellar explosion as a fixed measuring stick across billions of light years. Gravity has been pulling on everything since the Big Bang, so the expansion of the universe should be slowing down over time, gradually losing momentum, the same way anything thrown upward eventually loses speed as gravity drags on it. That is not what the data showed. The distant supernovae were dimmer and therefore farther away than a slowing expansion could explain. Expansion was not decelerating, it was speeding up. That result held up under scrutiny, replication, and decades of follow-up observation, and it forced a name onto whatever is causing it. Dark energy. Nobody has directly detected the thing itself. What exists is a measurement of its effect, calculated by tallying up the total energy content of the universe and finding that roughly 68 to 70% of it has to be attributed to this one unexplained component, driving space itself to expand at an accelerating rate rather than a decaying one. Here is the mechanism that turns that acceleration into permanent separation. Any galaxy not gravitationally bound to the local group sits in space that keeps stretching, and because the rate of that stretching is accelerating, the distance between us and that galaxy eventually grows fast enough that the space between shows up as receding faster than light itself can cross it. Light leaving that galaxy today will never arrive here, not because the galaxy is destroyed, not because anything violent happens to it, but because the room between us and it is expanding too fast for anything to bridge. That boundary has a name too, the cosmic horizon. Once a structure crosses it, contact of any kind becomes permanently impossible. Not difficult, not delayed, impossible. Run that mechanism forward using simplified expansion models, and the time frame involved lands somewhere on the order of roughly 150 billion years before every unbound structure currently visible in the observable universe has receded past that horizon completely. That is a number too large to hold on to with any real intuition, but the outcome it points to is easy enough to picture directly. Picture a future astronomer standing on a world orbiting whatever remains of the merged local group remnant, pointing an instrument at the night sky. There is one galaxy filling that view, the single bound structure this neighborhood eventually becomes, and beyond its edges there is nothing. No other galaxies to catalog. No superclusters, no cosmic web, no trace of the Great Attractor or Shapley or any of the vast structure currently mapped out across hundreds of millions of light years. Not because that structure never existed, but because every bit of evidence for it has already receded beyond any possibility of detection. That astronomer would have every reason to believe their galaxy is the only one that ever existed, and no instrument they could ever build would be capable of proving otherwise. That fading of the wider universe is not the final chapter, though. It runs on a clock that eventually intersects with something else. A much slower fade happening to the stars themselves, inside whatever galaxy is left standing once everything beyond it has gone dark. Stars themselves do not last forever, and the timeline for their final exit dwarfs everything covered so far. Meaningful star formation across the entire merged local group is expected to wind down somewhere between 10 to the 12th and 10 to the 14th power years from now. Numbers at that scale stop being dates and start being categories of time, stretching so far past anything measured in human history, or even past the current age of the universe itself, that comparing them to anything familiar loses meaning. The universe today is not even 14 billion years old. The window being described here is 100 billion times longer than that, and then some. Once that window closes and star formation finally stops for good, what remains behind is not empty space. It is a graveyard, though an orderly one. White dwarfs, the collapsed cores left behind by stars like the Sun, will drift for unimaginable stretches, cooling slowly but never quite going fully dark. Neutron stars, denser still, will keep spinning long after anything nearby has stopped producing new light. Black holes, patient and indifferent, will keep pulling in whatever drifts close enough. These three types of object become the entire population, the last residents of a galaxy that once held billions of active, burning stars. No new light gets added to that population. It only shrinks from here. Even that graveyard does not last. Push the clock forward far enough and a stranger possibility enters the picture, one that remains theoretical rather than confirmed. Proton decay. If the theory holds, ordinary matter itself is not permanent. Protons, the building blocks inside every atom, break down over timescales so long they make the age of stars look instantaneous by comparison. If this happens as some models predict, the white dwarfs and neutron stars left over from the stellar era do not just sit inertly. They slowly dissolve, atom by atom, until the ordinary matter that built stars and planets and everything else stops existing any recognizable form. Black holes get their own separate ending, one that is on far firmer theoretical footing than proton decay. Stephen Hawking's work showed that black holes are not eternal either. They radiate ever so faintly, losing mass at an agonizingly slow rate until eventually, over a timescale longer than anything discussed up to this point, they evaporate completely. The last black hole to form, the biggest and most patient object remaining, eventually follows the same path. It thins, fades, and disappears, leaving behind nothing but a diffuse spray of low-energy particles and radiation scattered across a universe that has by then stretched far beyond any structure at all. Sit with what that actually leaves behind. No stars, no structure, no galaxies, not even the single merged remnant that once held everything gravitationally close. Just a near perfectly uniform emptiness stretched across a span of space that has no edge and no landmark left standing anywhere inside it. Against a future that vast, it is worth turning back, deliberately, to what is happening in this exact moment, inside the one galaxy that still has all of this ahead of it, rather than behind it. 5 case files sit open on the table now. Start counting back through them, because the pattern only becomes visible once they sit side by side. The first file was invisible. A velocity nobody could explain, tracked back through the cosmic microwave background, through the 7 samurai, through a mass estimate that collapsed and rebuilt itself twice before settling into Laniakea and the dipole repeller working in tandem. Both of them dragging this galaxy toward a destination it will never actually reach. The second file was awake. A black hole confirmed by 2 teams on 2 continents, surrounded by objects that should not survive, and a barrier that should not exist, sitting quiet now, but carrying scars, gamma-ray lobes, and light echoes that prove it screamed within the last few hundred years. The third file was a collision, though the certainty around it did not survive contact with better data. A merger that may or may not happen, that may take 4 billion years or 10, or never arrive as a head-on impact at all, ending in a black hole binary that finishes its work in a fraction of the time it took to bring 2 galaxies together in the first place. The fourth file required no external cause whatsoever. A gas reservoir spending itself down, star formation fading toward a red and quenched future that thousands of other galaxies have already reached, a fate written into simple bookkeeping rather than any dramatic event. The fifth file was the largest and the quietest. An entire cosmic neighborhood sealing itself off, gravity winning close in the exact same moment that expansion wins everywhere else, until nothing remains visible beyond one merged, isolated remnant. Lay those 5 side by side and something is pulling us, something is dying inside us, something is leaving us behind. 3 separate sentences, 3 separate mechanisms, and not one of them needs a mistake to happen. No war, no accident, no external enemy required anywhere in this story. Gravity does this, time does this. Physics does this to every galaxy that has ever existed, on a schedule that has nothing to do with anything a species living inside one might do right or wrong. That is worth sitting with directly, because it removes the last comfortable assumption a person might reach for. This is not a threat that responds to caution. It is not a problem that gets solved. It is simply what a galaxy is, once you look at it closely enough and long enough to see past the illusion of a fixed, permanent night sky. And there is a strange kind of privilege buried inside that fact. Right now, at this exact point in cosmic time, the universe still holds enough structure to make any of this observable at all. The Great Attractor is still visible enough to be mapped. The Fermi bubbles are still glowing brightly enough to be photographed. Andromeda is still close enough to be tracked star by star. None of that stays true forever. The 5 threats catalogued across this investigation are not just things happening to the Milky Way. They are the last era in which a galaxy like this one can still be studied from the inside before isolation and fading and quenching. Each do their separate, patient work. All 5 threats trace back to the same fact stated at the very start of this investigation, the one that felt almost too simple to matter at the time. You are still moving right now at over 1 million miles per hour, exactly as you were when this began. Nothing about that has paused while you sat here listening. The floor beneath you has not stopped. The galaxy carrying you has not slowed. You feel none of it, the same way you felt none of it at the start. And that gap between what your body senses and what is actually true has been the real subject of everything covered here. The Milky Way is not stable. It never was. It only looks that way from the inside, the same way a ship's deck looks perfectly still to anyone standing on it mid-ocean. Every measurement taken across every chapter of this investigation points the same direction. A pull with no visible source. A core that has erupted before and carries no promise of staying quiet. A neighboring galaxy on a course that used to be certain and no longer is. A fuel supply spending itself toward a red and quiet future. A boundary already forming around everything this galaxy will ever be allowed to keep. None of that arrives today. None of it arrives this year, or this century, or across any span of time a single life could measure against. But it is already running in this instant the same way it was running in the instant Penzias and Wilson first heard a hiss they could not explain. The same way it was running when Karl Jansky pointed an antenna at a field in New Jersey and caught a signal aimed at nothing else in the sky. This is what a galaxy in the middle of its life actually looks like up close. Not frozen, not finished. Fully alive, fully structured, filled with stars still igniting and a core still capable of waking. Held together by gravity that will not hold forever. Moving through a universe that is quietly pulling everything else out of reach. It will not look this way again. Not from here, not for anyone standing where you are standing now. And somewhere beneath all of it, carrying you forward whether you notice or not, the motion continues in this exact instant. As you finish this sentence,